Some signals only appear when features interact. Polynomial features makes those crosses explicit, so a linear model can actually use them. You'll learn how the pieces fit into a workflow that learns cross-powered weights and predicts boosted study scores. I'm Professor Pi, teaching AI foundations with simple Python. Linear models are fast and easy to inspect, but they miss effects that only show up when inputs combine. Imagine hours studied and number of practice problems. Each helps a bit alone, but together they can produce a jump in score. Polynomial features simply creates those combined terms, so a linear learner can weight them directly. At the heart, polynomial features builds new columns that multiply or power your inputs, so the linear model actually has the right basis to fit. The downside is obvious. More columns. That's fine for small, controlled examples. But on messy real data, you'll want regularization or feature selection. We'll run a compact example where the true rule rewards pairs of study factors. First, we'll show a plain linear fit failing, then add crosses to recover the pattern cleanly. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. To start, fit a baseline linear regressor on the raw features so we can see the missing interaction. This snippet fits scikit-learn linear regression on raw features to show a missing interaction signal. It loads toy hours into X, computes the product-based target Y, and fits linreg without any interaction term so we can see the systematic error the learner leaves behind. Baseline MSE captures that residual pattern and gives us the number to beat when we add interaction features. The baseline shows a clear gap, so the next step is to expose interaction terms so the linear model can represent multiplicative effects. This example wires scikit-learn polynomial features into the pipeline, so linear regression can see explicit degree 2 crosses. We expand X into X poly with poly, fit lin poly on that matrix, and set include bias false so the estimator's intercept isn't duplicated. Degree equals 2 mixes pairs without blowing up the feature count. Higher degrees add cubic and higher orders quickly. Poly MSE drops to nearly 0, which confirms the interaction term closes the error we saw earlier. We should check that this improvement generalizes beyond the training points, so we validate on held out examples. This code checks both regressors on fresh points to illustrate how interaction features change holdout rankings. We build xeval from the same product rule, transform it into xeval poly, then score linreg and linpoly with mean squared error so the comparison is fair. The conditional best model expression picks the winner for us, and holdout best flags whether the interaction enhanced regressor actually generalizes. The full quadratic expansion includes squares that are sometimes redundant. If you only want crosses and fewer columns, trim the expansion. This snippet trims scikit-learn polynomial features to interaction only to keep useful crosses without redundant squares. Swapping in polyinter gives xinter with just the pure cross columns. Lininter trains on that smaller set, and xevalinter plus interpred confirm the holdout fit stays tight. Keep in mind, interaction only, true, still grows features with degree through multi-way crosses, so check interaction MSE and the features count to make sure each extra term is worth the cost. Now, make the workflow robust by locking transform and estimator together, so inference cannot forget the expansion. This example packages polynomial features and linear regression into a scikit-learn pipeline for a tidy final baseline. The two-step list wires poly expansion to the model, fit trains the pair on X and Y, and mean squared error checks the holdout match. You can change degree inside the pipeline to explore richer crosses. But remember, each bump adds columns that may require regularization later. Pipeline MSE, landing at 0, shows the packaged baseline, preserves the interaction fix for consistent inference. In a real project, you would map hours and practice counts to real features like minutes on task and number of graded problems. The same approach applies. When you suspect multiplicative or joint effects, expose them with polynomial features, and then add regularization or feature selection as the feature set grows. Polynomial feature crosses make explicit products and powers, so a linear model can learn joint effects. Use them when small groups of inputs interact and you want to keep a simple, interpretable learner. The trade-off is dimensionality. Degree increases add columns fast, so plan to regularize or prune as you scale. Next step, tune degree and add a regularized linear model so you can safely explore richer crosses without overfitting. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.